Okay, we're going to make a start now. So welcome everyone to our maths group session. Um, in today's lesson, we are going to be looking at harder circle theorem questions. So in our lesson before our last lesson, we looked at circle theorem questions. We had sort of a nice intro to circle theorems, and in today's lesson, we are going to be focusing on harder circle theorem questions. So circle theorem questions, which are more multi-step questions, and also some algebra in circle theorems questions towards the end of today's lesson. If you have any questions at any point, you can let me know in the Q&A. If you don't have access to the Q&A, there is a QR code on the screen which you can scan to have access to the Q&A. Okay, so you can let me know your responses through that. What we're going to start off with is going through this question. Okay, so this was a multi-step question and we had it at this end of our last lesson, but we didn't quite get through it in our last lesson. So we're going to start off by looking at this question. So I've got this question over here. We're going to start going through it. So it says A and C are points on the circumference of a circle, center O. And it says AB and BC are tangents to the circle. It says angle ABC is 46 degrees. It says find the size of angle OAC and give reasons for each stage of your working. So that's what we have to do for this question. If we look at it step by step, and we need to give our reasoning for each part of the answer. Okay, so let's have a look at this question over here. It says ABC is 46 degrees, which we can see clearly. A, B, and C is 46 degrees over here. Now, what can we see? What can we spot in this question? Straight away, we can spot that we have a center over here. This is our center, and we can see that we have a center that is meeting the circumference of the circle. When we have a center that is meeting the circumference of the circle, that is called a radius. So this line that I've drawn from O to A is the radius of the circle. Okay, so this is a radius, and we can see OC is also a radius. So from the center all the way to C, that is also a radius. Now we know that this is a radius and we know that this is a radius, which means that both of them must be of the same size. Okay, so this side over here is the same length as this side. And then we've got a line which is connecting the two radii up together, which means that if we have a triangle like this and we have two sides which are the same length, we know that this is going to be an isosceles triangle. And if we have an isosceles triangle, we know that opposite sides in an isosceles triangle are the same. And if opposite sides of the triangle are the same, we also know that the angles which are opposite to each other are also the same. So these two bottom angles, they are also going to be the same. Okay, so we know that these two sides, the radii, they are the same. We also know that this angle and this angle are going to be of the same length as well. Okay, so that's what we've spotted first of all. Next, we can see that we've got point B over here, and the point B, there's a line which is extending. We can see that a line is coming and it's meeting the circle. Okay, and I'm going to draw it in a different color. We've got this line over here coming from this point over here, and it's meeting at this point, at point C. Okay, that's what we have. And we can see that when you have a line which is coming in and it's meeting the tangent, it's meeting the circumference of the circle, we know that that line is going to be a tangent. So we know that a tangent is coming in. We can see a tangent sort of coming in and meeting the circumference of the circle. Okay, we can see that another tangent is coming in and it's meeting the circle on the other side. Okay, on this side from B to A. Okay, so we can see two tangents, and the rule that we know in terms of a tangent meeting the circumference is that they meet at a right angle. When a tangent meets the radius at the circumference, a right angle is formed. Okay, so we can see that this angle over here is a right angle that is formed. Okay, this angle that is there is a right angle. Okay, because we have a radius and it's meeting a tangent. So we've spotted those things. What do we need to work out in this question? We need to work out the size of angle OAC. Now, size of the angle OAC is this one over here. Again, I'm going to switch color. Is this one over here, OAC. Okay, that's what we need to try work out. So I'm going to get rid of my annotations and we're going to work through this again from the start. So we know that this is an isosceles triangle. We know these two sides are equal. That's x. Okay. Now, what we can see over here is that this is 90 degrees because it's a radius meeting a tangent. And this is also 90 degrees because it's a radius that is meeting a tangent. We can see a quadrilateral that is forming over here, BAOC. Okay. And we know that angles in a quadrilateral add up to 360 degrees. Okay, so angles in a triangle add up, in a quadrilateral add up to 360 degrees. We know that this is 90, we know that this is 90, and we know that this is 46. Okay, so we need to work out what this angle is, and then we can work out the next stage of the question. Okay, so we know that we have 46, add 90, add 90, add something, and that's going to get us 360. Now 46 add 90 at 90 is going to get us 226, and 226 add something equals 360 degrees. Okay, so to work out what the x is, we do 360 subtract 226, and that gives us an answer of 134 degrees. So angle AOC is 134 degrees. Okay, so we've worked our angle AOC. Now, if we draw out that triangle once again, we can see that we have this triangle. I've just drawn out that triangle that you can see. We know that the top angle over here is 134 degrees. We need to work out what this angle is to the left. But we know that both of these angles, because it's an isosceles triangle, they are the exact same. Okay, so we know that angles in a triangle add up to 180 degrees. So we know that if we do 180 subtract 34, 134, that's going to get us an answer of 46 degrees. Okay, and that is split between these two angles. We know that both of them are the same. So if this one's x, this one's also x. So we know that the sum of both of those angles is 46. So that means to work out the sum of the angle, one of the angles, you have to divide by 2. So 46 divided by 2. And that's going to get you 23 degrees. And that's what the answer to this question is. It is 23 degrees. Now, I know I've not written down the explanation, but the rules that you would need to get the full marks on this question is, first of all, spot that a tangent meeting a radius at 90 degrees. So we can see that we have a radius here and a tangent meeting a radius. That's 90 degrees. Okay, you then need to spot angles in a quadrilateral add up to 360 degrees. And then you need to write down the angles in a triangle add up to 180 degrees, and opposite angles in an isosceles triangle are the exact same. Okay, so that's what you would need for a question like this. Okay, again, this is a multi-step question, so it's one of the more harder questions that you could get. We're going to be looking at more harder questions in today's lesson. Okay, and we're going to be slowly increasing the difficulty as we move through the lesson. So, moving on, I'm going to give you guys an opportunity to have a go at these questions first, and then I'll be going through them. So this is the question. I want you guys to have a go at this question. I'll give you guys a couple of minutes, and then I'll slowly go through the answers. Once you have an answer, let me know in the chat, or if, well, in the Q&A. If you don't have access, there's a QR code again to let me know what your answer is. Okay, I will start going through it in about 2 minutes. Okay, guys, I'm just going to give you guys 1 more minute, and then I'm going to start going through the answers. With multi-step circle theorems questions, it's about spotting which rules are being used. Can you spot what's happening in the question? The easiest ones, whenever you see a radius, spot the radius. Meeting a tangent, you know it's 90 degrees. Okay, so I'm going to slowly start going through this question. If you're still going through, having a go at it, keep on having a go at it and type your answer when you have one. So it says over here, A, B, and C are points on the circumference of a circle, center O. So we have our center O over here, and A, B, and C, they are points on the circle, A, B, and C. Okay, it says BD and CD are tangents to the circle. Now, one thing you can see over here, when we have O to B, this is a radius because we have a center, a line going from the center all the way to the circumference. Okay, and over here we have a line going from the center to the circumference. So both of them are radial. Okay, it says we have a tangent meeting the radius. So again, we have a tangent coming from D all the way to the radius. Okay, so a tangent appearing from D. Now, when a tangent meets a radius, we know that the angle which is formed is 90 degrees. So we have a 90-degree angle which is being formed. Okay, so that's one of the most easiest rules to spot out. So please make sure that you do spot out these rules. These are important rules. Okay. Then it says over here, we know that this is 26 degrees and we have a line which is going in the center. Okay, now again, you have to spot the rule that is going on over here. It says this is 26 degrees, and if we think about it, it's symmetrical. This we've got a 90-degree angle which is formed here and a 90-degree angle which is formed here. So if both of these angles are the same, that means that the size of the angle BDO is also going to be 26 degrees. So this is also going to be 26 degrees. Okay, so those two are 26 degrees. These two are 90 degrees. We need to work out the size of angle BAC, which is this one over here. Okay, now we can see that another rule is emerging over here. We can see that we have this shape over here. And when we have this sort of shape, you know that the angle at the center is going to be double the angle at the circumference. Okay, so we have this sort of shape, which means that the angle at the center is double the angle at the circumference. Okay, so that's what we have. Okay, now we know that this is 26 and 26, which means the whole green angle that we have is 52 degrees. 52 degrees. We know that this is 90 degrees, this is 90 degrees. We can work out this angle. Okay, and we know that we can work out the angle because we have a quadrilateral. Again, if I switch color, we have 1, 2, 3, 4. We have 4 sides. So we know, well, let's quickly just note down the rules that we've used over here. We know that angles in a quadrilateral add up to 360 degrees. We also use the rule that a tangent meets a radius at 90 degrees. Okay, I'm not exactly sure which year this past paper is from. I've used a mix of past paper questions. I can't remember exactly which year this is from. Okay, and I've also used questions from like specimen papers, that sort of stuff as well. Okay, so over here, we know that angles add up to 360 in a quadrilateral. So we know that 52 at 90, at 90, at something, that green angle is equal to 360 degrees. Okay, that's what we know. So we have 90 at 90 at 52. 90 at 90 at 52 gives you 232. At something gives you 360 degrees. So you do 360, subtract 232, and that gives you 128. So that missing angle is 128 degrees. So this over here is 128 degrees that we have. Now we know that the angle at the center is going to be double the angle at the circumference. Now, because the angle at the center is double the angle at the circumference, we know to work out this angle, which is our unknown angle, we would need to halve the angle which is at the center. So we would do 128 divided by 2. And that's going to get you an answer of 64 degrees. And the explanation for that is that the angle at the center is double the angle which is at the circumference. So again, multi-step question. Again, the easiest rule to spot is the tangent meeting a radius. You can see that tangent was meeting a radius, spot that that's 90 degrees, and then you make your life much easier. You know the angles in a quadrilateral add up to 360 degrees, and then you're going to use the circle theorem that says that the angle at the center is double the angle at the circumference, because you can see that shape appearing in the triangle. Okay? So moving on, we're going to look at our next question. So again, we're increasing the difficulty. So we've got this question. Okay, again, I want you guys to have a go at it first. I'll give you guys a couple of minutes and then I'll start going through the answers. Okay, this is a more difficult question compared to the previous ones we have looked at. Okay, just one more minute and then I'm going to start going through the answer. Okay, so I'm going to start going through this question now. If you're still having a go at it, continue having a go at it, and then type your answer into the Q&A once you're done. Okay, so now this is slightly more difficult, and one of the reasons why this is more difficult is because there is a rule that is in here that everyone struggles with, and that is the alternate segment theorem. Okay, the alternate segment theorem is going to be applied for this question. Okay, and another thing over here, it says find the size of angle AOC. Okay, and there is no line connecting A to O to C because there is no angle, there is no corner to work out the angle. In that case, they can ask you questions like this. You have to draw in the line yourself because that question is actually giving you a clue to work out the answer. So it says AOC, draw in the line yourself. So AOC is A to O and then O to C. So we're trying to work out the size of this angle. That's angle X. And in doing so, again, with circle theorems, an exam technique that you can use is make yourself triangles. The more triangles you make, the easier your life will be when answering this question. Okay, because most of the triangles that you make will be isosceles triangles. So as you can see, we've got center O, and that is meeting with A, the circumference, so that is the radius, and OC is also a radius. So that means these two sides are equal, which means that these two angles are also going to be equal. Okay, so the question has actually given us a clue here to work out the answer. Now, when you have a question like this, like a tangent and a triangle, the alternate segment theorem is going to come into play. And remember what the alternate segment theorem says. Okay, we looked at it in our last circle theorems lesson. Let's say we have a line like that. When we have a line like that, we know that this line is the chord. This line is called the chord, and the chord splits the circle into two segments. You have the major segment, which is the bigger area, that's the major segment, and then you have a smaller area, which is the minor segment. So this area over here is the minor segment. So you have the major segment, and then over here you have the minor segment. There are two segments that you have. So over here, in this example, there is also a chord that you can see. You can see the chord over here. This is your chord. Okay, that is one chord that you can see. And you can see that there is a major segment to the left of it, and then there is a minor segment to the right of it. And what does alternate segment theorem mean? Alternate segment theorem means that the angle in one segment, the angle which is opposite that in the other segment, is going to be equal. Okay, so for example, in this question, we can see that we've got this angle over here. We've got 65 degrees on this side. Okay, it's in the right segment. That means the angle which is opposite it is also going to be the same in the opposite segment. Okay, so we've got 65 degrees. This is in the minor segment because it's in the smaller segment of the circle. The angle which is opposite it in the other segment is going to be equal. And the angle which is opposite this angle is this angle that we have over here. This angle is in the opposite segment to BCE. So we knew that this was 65 degrees. The angle which is in the opposite segment is over here. So that means this red angle that I've drawn is going to be 65 degrees. Okay, and that's the hardest part of this question. If you can spot that, then you will progress like far in this question. So that is the alternate segment theorem. Okay, let's say we have so over here this you have your minor segment. So over here, this area is your minor segment, and the area which I haven't shaded in, that's your major segment. Now, there is another thing which many people don't realize. Now, if you tilt your head, you can see that you have a big isosceles triangle. You can see that there is an isosceles triangle. A to B, we have this. B to C, we have this. And then A to C, we have that. We can see that there are these two lines over here. And these two lines tell you that it's an isosceles triangle, which also tells you that these two angles, we worked out that this is 65 degrees. That means that this angle over here must also be 65 degrees. Okay, so this angle over here must also be 65 degrees because it's an isosceles triangle. That's a key fact that you need to make sure that you note it down. You have to notice that it says these two lines are equal, which means that it's an isosceles triangle. Okay, now we know that that's equal. There is another rule that you should be able to see. You can see that DCE is a straight line. Okay, you can see that D to C to E is a straight line. And we know that angles on a straight line add up to 180 degrees. So that means if this angle here is 65 degrees, this angle here is 65 degrees, we can work out what this angle here is going to be. And to work out what that angle is going to be, you're going to do 65 at 65. That's going to get you 130. And then 180, subtract your 130. You know that this angle is going to be 50 degrees. Okay. Now, you need to work out this x over here. And to work out x, you have a small isosceles triangle over here as well. You need to work out the size of these two angles that we have. These two angles that are in green. We need to work out the size of this angle, and we need to work out the size of this angle because both of these angles are going to be the same. We know that this distance is 50. We know that this distance over here is 65 degrees. But there is another rule. That's why this question is confusing, because you have a radius over here and it's meeting a tangent. And a radius meets a tangent at 90 degrees. Okay, so this over here is 90 degrees. Now we know that this distance is 50 degrees. So to work out this distance, we know that it's going to be 90 subtract 50, which is just going to be 40 degrees. So this distance over here is going to be 40 degrees. And because it's an isosceles triangle, you know that this angle is going to be the same as this angle over here. Both of them are going to be 40 degrees. So now you can work out what x is going to be. You're going to do 40 at 40, that's going to get you 80, and then you're going to do 180, subtract 80, that's going to get you 100. So that means that x is equal to 100 degrees because you have opposite angles in an isosceles triangle. We're looking at Harder circle theorems in today's lesson. Okay, so this was a difficult question. It's one of the most difficult questions that you could be asked. In terms of algebraic circle theorems, those are hard as well, but in terms of with number calculation questions, this is probably the hardest number calculation question you could get in terms of circle theorem. So if we quickly note down the rules that we went through, first of all, we realized that we needed to use the alternate segment theorem. Okay, so step one, we used the alternate segment theorem. And the alternate segment theorem states that an angle in one segment, the angle which is opposite to it in the other segment is going to be equal. So you had this red, the red lines that I've drawn is the minor segment. So this is your minor segment, and we had an angle which was given, it was 65 degrees. The angle which is opposite it in the other segment across the chord, remember this line over here is the chord, this line that we had over here, that was the chord, that's going to be 65 degrees. So we saw that this whole angle that we had over here was 65 degrees. Okay, then once we figured that out, we then saw that angle BCA is also 65 degrees. So we saw that BCA is also 65 degrees. And the reason why it's also 65 degrees is because opposite angles in an isosceles triangle, we saw that it was an isosceles triangle, opposite angles in an isosceles triangle are equal. In an exam, you should be fine in saying alternate segment theorem. You don't need to give that full explanation. If you're giving a reason, alternate segment theorem should be sufficient. Okay, because opposite angles in an isosceles triangles are equal. Okay. Then once we figured that out, we saw that opposite angles in the isosceles triangle were equal. We saw that we calculated this 50 degrees. We saw that angles on a straight line add up to 180 degrees. So angles on a straight line add up to 180 degrees. And then the other rule that we saw was that we had a radius meeting a tangent at 90 degrees. Okay, so we saw that a radius meets a tangent at 90 degrees. And then we use the rule that opposite angles in an isosceles triangles are equal, and angles in a triangle add up to 180 again when we were working out x of the smaller isosceles triangle. Okay, so that was a difficult question, and that is probably one of the most difficult questions I've seen come up in an exam paper, in a higher tier paper. Now, what we're going to do is we're going to have a look at this algebra one. Now, algebra ones, some of them can be easier than this question, and some of them can be at the same difficulty. They've literally, all they've done is they have replaced the numbers with letters. Okay, that's all they have done to for questions like this. So it's nothing to be bogged down by. You follow it in the same exact way, but this time you're using algebra. So you don't have specific numbers. Okay, so I'll give you guys an opportunity to have a go at this first, and then I'll start going through the answers in a couple of minutes. Okay, so I'm going to start going through the answers now. So again, this could be a question that you could get. When we first of all look at this question, what do we see? Okay, now when you look at this question, you can straight away see that you have a quadrilateral in play. You have a quadrilateral in pay. You can see A, B, C, D. They are all touching the circumference. Because they are all touching the circumference, it is a quadrilateral. And you know that the circle theorem, which applies for a quadrilateral, is that opposite angles in a cyclic quadrilateral add up to 180 degrees. Okay, another thing that you can see in this question is that shape again, this shape over here. The shape where the angle at the center is double the angle at the circumference, or the angle at the circumference is half the angle at the center. Okay, now let's read the question. We've spotted what we can see straight away from this question. It says A, B, C, and D are points on the circumference of the circle center O. It says angle BOD is X. Find the size of angle BCD. Okay, so this is the angle that we need to find out. This is our unknown. Okay, I'm not going to put X because we already have an X. That's our unknown there. We need to give reasons for each stage of our working. So first of all, we can see that shape. So what we can do is that we know that this is X, and we know the angle at the circumference is half the angle at the center. So if this is X, that means that this angle over here is going to be a half of that. It's going to be a half of X. You can write a half X or X divided by 2, anything like that. So let's explain that. So we know that angle BAD is equal to a half X. Why is it equal to a half X? It's because that the angle at the circumference is half the angle at the center. Okay, so we have worked out what angle BAD is. We need to work out what this BCD angle here is. And we can spot that we know this angle, angle A, and we know that angle C is completely opposite to angle A, which shows that it's opposite angles in a cyclic quadrilateral that we're looking for. Okay, so we know that angles, opposite angles in a cyclic quadrilateral, they add up to 180 degrees. So that means something at a half x must equal 180 degrees. Okay, so to work out that something, we know that we need to subtract a half x from both sides to get that something by itself. So we have the something is equal to 180 minus a half x. Okay, and that's what our answer is going to be. 180 minus a half x. Okay, and we need to leave our answer in terms of x, and we have left it in terms of x. And our reasoning for it is that opposite angles in a cyclic quadrilateral add up to 180 degrees. So opposite angles in a cyclic quadrilateral add up to 180 degrees. Okay, so that's what we have for a question like this. Again, if you were to ask me in terms of difficulty, which question was more difficult, this question or this question, I'd easily go this question. This question was more difficult than this question. This question, you only needed to spot the two rules. Over here, you were given the numbers. However, there were so many more rules that you needed to know to answer this question. And finding those rules was more difficult in this question than was in this question.